Hello viewers, welcome back to this channel. So in this video, we're going to be proceeding our physical chemistry, handling structure and bonding as a topic in physical chemistry. So this video is going to be presented to you by Olgembe Yusuf, and your advice: share the video to friends, subscribe to the channel, and share the video to friends so that you can all benefit as a family. Now, handling structure and bonding, we are going to be starting with identifying some of the structures that we are having under structure and bonding, because identifying these structures is going to help us improve our inorganic chemistry. Remember that for structures, when you're looking at structures, structures are very important in explaining melting points and boiling points, which are full topics or which are full numbers, full examinable numbers under inorganic chemistry in each and every group, and also the periods. So let's start with the giant ionic structures, and here we are going to be saying that in giant ionic structures, metallic elements combine with non-metallic elements. That means that for us to have an ionic compound, we must have a metal combining with a non-metal, and by the bonds that are formed between a metal and a non-metal are going to be called ionic bonds, and such a compound that is being formed is going to be called an ionic compound. And therefore we consider that ionic compounds, their structures are going to be called giant ionic structures. So proceeding, we are going to be saying that the ionic bonds formed in these compounds are strong electrostatic attractions that are formed between the ions of the positive or the ions of the opposite charges, and that is to say those of the cations and those of the anions. So we shall continue and say that each ion is going to be surrounded by the greatest number of the oppositely charged ions, which is being called the coordination number. And you're going to be looking at the coordination number more in details under the topic of transition elements, which is going to be the next video to be uploaded after completion of the videos under structure and bonding. So we're going to say that examples of ionic solids or ionic compounds are going to include the following. Remember that I told you for ionic compounds to be formed or for ionic bonds to be formed, it must be between a metal and a non-metal. So examples, we have sodium chloride. Sodium chloride is formed when the metal is sodium and the non-metal is going to be chlorine. We have calcium chloride, and we also have zinc blend, which we shall look at under extraction under transition elements, or extraction of transition elements. So look at the covalent character of ionic compounds, which is the most commonly examined concept under U.A.C.E examinations. So we're going to be saying that the partial covalent character of an ionic bond is explained in terms of polarizing power, and polarizability, polarizing power and polarizability. So we're going to define the two terms, but you need to understand that for an ionic compound to have characteristics of covalent compounds is because of these two factors, which is polarizing power and then polarizability. So starting with polarizing power, the key takeaway before we start this one is going to be that polarizing power is explained in terms of cations or ions of metals, because they are the ones that have the ability to polarize the other ions, which are going to be the anions. So we're going to say that polarizing power is going to be the power of a cation to distort the electron cloud of an anion. Is the power or the ability of a specific cation so as to distort the electron cloud of a specific anion. So we're going to be saying that the greater the polarizing power of the cation, the greater the tendency of the cation to form a covalent bond. So that means that, for example, if you're having an ionic compound, for example, aluminium chloride, aluminium cation in aluminium chloride is having a charge of +3. So we call this one having a higher charge density. So the higher the charge density, the smaller the ionic radius and the greater the polarizing power. So that means that aluminium chloride is going to dimerize in air, because aluminium ion in aluminium chloride has a very high charge density together with a small ionic radius, which are very crucial in increasing its polarizing power over the chloride ion. So it greatly polarizes the ionic bonds within its molecules or within its compound, forming a partly covalent compound, as we are going to be looking at the specific examples. So continuing or proceeding, we are going to be saying that polarizing power of a cation is going to depend on the following factors. You have been hearing me talking about the charge, which is the charge density of the cation. We're also going to be looking at the ionic radius. Now what you should note here is that the higher the charge on the cation, the smaller the ionic radius, and the higher the charge density. So charge, ionic radius, and charge density are linked when you're explaining what you call anything involving polarizability. So looking at the charge, you're going to say that cations with high charges have high polarizing power. And the larger the positive charge that is present on the ion, the greater the attraction of the valence electrons. For example, the aluminium ion has a higher polarizing power than the sodium ion due to its higher charge. So the greater the extent of the charge, or the greater the magnitude of the charge present on a specific cation or any ion of a metal, the higher the power of polarization, or the higher the polarization power. And then let's look at cationic radius. We are going to be saying that here, the smaller the ionic radius, the higher the polarizing power of the cation. So implying that any cation which has a high charge density, for example aluminium, we expect it to have a smaller ionic radius because the two are linked together, or they are directly proportional. The smaller the ionic radius, the higher the charge density. So we're going to be saying that aluminium ion therefore has a higher polarizing power than the sodium ion, due to aluminium having a smaller ionic radius as compared to sodium ion. Now remember that aluminium and sodium are in the same period, and we say that at radius or ionic radius decreases across a period. So looking at factor 3, we are going to look at charge density, or the charge to radius ratio. So we're going to say that the charge density is going to be the ratio of the ionic charge together with its ionic radius. So some of you asked to find this question, especially in mocks, and majority of you fail to get this solution right. For you to calculate for charge density, you get the ionic charge which is present on a specific cation, and then you divide it with its ionic radius. So whenever such questions are to be examined, you'll be provided with the ionic radius, and you'll be provided with a specific ion. So simply, if you are to calculate for polarizing power or charge density of the sodium ion, we are going to get the charge which is present on it, which is +1, then divided by the magnitude or the ionic radius, which is 0.095. And doing that and putting everything in the calculator is going to be 10.53, and the SI unit is going to be per Newton meter. Similar applies to magnesium. Now notice that you don't need to carry the +2 or the charge which is present. You just need to carry the magnitude of the charge. So we carry 2, don't place the positive there. So 2 divided by the ionic radius of magnesium is going to give us what we call the charge density. Also, for charge density of aluminium, we get 3, which is the charge, divided by its ionic radius, which is 0.05, which is going to give us what we call the charge density. And that's how we calculate for charge density. So the key takeaways here, you should always remember that polarizing power is going to be explained in terms of 3 factors. And the first factor is going to be the charge which is present on the cation in a specific compound. The other factor is going to be the ionic radius. And I've told you that the higher the charge, the smaller the ionic radius, and therefore the greater the polarizing power. And therefore, if at all the charge is higher and the ionic radius is smaller, we also expect that charge density is going to be higher, just like we have calculated. From these examples, you can see that aluminium, which has a higher charge, has the highest charge density, and magnesium, which has the medium charge, has the moderate charge density, and sodium, which has the lowest charge, has the lowest charge density. So the higher the charge, the smaller the ionic radius, and the higher the charge density. So you should know how to use these 3 factors in explaining terms concerning polarizability. Now let's look at the examples to see how we can implement this one correctly under the questions that will be asked specifically. So looking at a well-explained example, we are going to be saying that the higher the charge density, the higher the polarizing power of the cation. And you're going to say that from the table above, explaining what you have given above, the charge density and from the table above, charge density and hence polarizing power is going to increase in the following order, just like I've explained. Aluminium is going to have a higher charge density than magnesium, and magnesium is going to have a higher charge density than the sodium ion. So we're going to say that covalent character of their chlorides, of their ionic compounds formed by the elements is going to be increasing. For example, if you're having chlorides, its covalent character is going to be increasing from sodium chloride to magnesium chloride to aluminum chloride. And this statement means that aluminum chloride is going to have the highest covalent character, followed by magnesium chloride, followed by sodium chloride. And that's because of polarizing power. Now you should know, under this topic, you should know the characteristics of covalent compounds. We looked at covalent compounds to have to melt or boil. Covalent compounds have low melting or boiling points, and that's as a result of polarizability, which we explain in three terms. So we're going to say that in general, compounds in which the cation has a high charge, we expect it to have a small ionic radius, and therefore it's going to tend to have a high charge density. And once it has all those three components, or all those three factors that we previously explained, we are going to assume that it's more likely, or it's going to have a high polarizing power. So we're going to say that having those three factors is going to make the compound to have a high polarizing power. And once there's a very high polarizing power within an ionic compound, it's going to make such compounds to tend to have covalent character. And therefore, we expect such ionic compounds to exhibit ionic character, to exhibit properties that are contrary to ionic compounds, or to exhibit properties that are similar to covalent compounds. For example, such ionic compounds will be able to dissolve in polar solvents, which is not a characteristic of the ionic compounds. So we are going to give characteristics of such compounds that have covalent characteristics, or that form characteristics that are contra to characteristics of ionic compounds due to high charge density, small ionic radius, and high charge present on the cations within such compounds. So if you look at aluminium chloride, we expect that aluminium here has a small ionic radius and high charge together with high charge density, which gives it a high polarizing power of the whole compound, and therefore the whole compound is predominantly covalent. Similar applies to beryllium chloride, similar applies to aluminum hydride, similar applies to beryllium hydride, and similar applies to beryllium oxide together with beryllium hydroxide, which are partly covalent for reasons explained above. So now let's look at the other part, which is going to be polarizability. Now we have been looking at polarizing power. Now polarizability is going to be about the anion. Polarizing power is for the cation. Polarizability is going to be about the anion. So whenever I see about concept telling you to explain polarizing power, it requires you to give an explanation in terms of cations. But if at all the question is in terms of explaining polarizability, then your explanation must be in terms of the anions. So we are going to start with the definition, and it says that polarizability is going to be the ease by which the electron cloud present on the anion can be distorted. So the ease by which the electron cloud of the anion can be distorted is going to be called or termed as the polarizability. And we're going to say that the greater the polarizability of the anion, the greater the tendency of the anion to form a covalent compound. So that means that for us to have an ionic compound which is highly covalent, then the anion must be easily polarizable. And for an anion to be easily polarizable, we look at the atomic radius or the ionic radius of the anion. the larger the size of the ionic radius of the anion, the greater or the easier it is to be polarized by the cation. We also look at the electronegativity. You'll see that anions with higher electronegativity are not easily polarized as compared to anions with lower electronegativities. So you're going to say that polarizability of anion depends on the size of the anion, which is the ionic radius, which I've already talked about. And you're going to say that the smaller the anion, the smaller the size of the anion, or the smaller the radius of the anion, the lower it is to be polarizable. And the larger it is, the easier it's going to be polarized. So you're going to say that if you consider the halide ions, polarizability is going to be increasing this order. And the reason why it is increasing in this order, iodine is going to be easily polarized compared to bromide, and bromide is going to be easily polarized compared to chloride, and chloride is going to be easily polarized compared to fluoride. And the reason why it is this in this case is because iodine is the easier to be polarized because iodide ion has the largest ionic radius. And bromide ion also has the larger ionic radius as compared to chlorine, which is the same with chlorine and fluorine. So fluorine having the smallest ionic radius, it is not easily polarized. So we expect that ionic compounds involving the fluoride ion are more ionic compared to those involving the iodide ion, because the iodide ion can easily be polarized. So we are going to be looking at the examples to show the effect of the polarizing power of the cations and together with polarizability of the anions. So don't forget that here I say that polarizing power is concerned with cations, and then polarizability is concerned with anions. So we're going to say that the table below is going to show the melting points of the chlorides formed by the three period 3 elements. So if you're having a chloride, you're going to have sodium chloride, you're going to have magnesium chloride together with aluminum chloride. So you're also going to have the melting point of the chloride. For sodium chloride, the melting point was given to be 801. For magnesium chloride, melting point is 712. And for aluminum chloride, melting point is 180. Now I told you when you're dealing with these ionic compounds, when they have given you their melting or boiling points, you have to understand characteristics of ionic compounds and also characteristics of covalent compounds. We say that ionic compounds have higher melting and boiling points, and covalent compounds have lower melting and boiling points. In fact, they have the least melting and boiling points. So if you see an ionic compound having a very low melting or boiling point, that means that there is a component of polarizability or polarizing power by the cation in that compound, which distorts the ionic bonds to make the whole compound partly covalent. So the explanations are going to be in this format. So since the question is saying state and explain the trend, we start by stating the trend before explaining it. So stating the trend is going to be that melting points of the chlorides are going to decrease from sodium chloride to aluminum chloride. And after stating that, you're going to say that sodium chloride and magnesium chloride have giant ionic structures. Remember that when you're explaining melting points, just like we looked at it in ionic chemistry or in organic chemistry, you must first state the structure held by the different elements. After stating the structure held by the different elements, you talk about the forces that are holding that structure. After talking about the forces that are holding that structure, you talk about the strength on which those forces depend on. If you're having a giant ionic structure, that means that it's being held by ionic bonds, and ionic bonds, they depend on ionic radius, or the radius that is present between the ions that have combined, together with the opposite charges, magnitude of the opposite charges present in such a compound. So let's look at the general explanation according to what the hints I've given you. So we're going to say that sodium chloride and magnesium chloride have giant ionic structures, which are held by strong ionic bonds, and therefore they are going to require a very high amount of energy to break. So we're going to be saying that the decrease in melting point from sodium chloride to magnesium chloride is because magnesium ion has a smaller ionic radius. You remember what I told you. So if you look at this, what was varying is the cation. And since it's a cation that is varying, that means that you're talking about polarizing power. If it was the anion which was varying, then you'll be talking about polarizability, just like I emphasized earlier on. So you're going to say that from sodium chloride to magnesium chloride, a decrease in melting point is going to be because the magnesium ion has a smaller ionic radius together with a high charge density and high polarizing power. So notice that whenever you're talking about charge density, high charge density, you always have to talk about smaller ionic radius. They move together before you conclude on the magnitude of the polarizing power. So the magnesium ion having a higher charge is going to have a smaller ionic radius and a higher charge density together with a higher polarizing power than the sodium ion due to the reasons that we explained above, making magnesium chloride less ionic, because if at all the cation has a higher polarizing power, it's going to distort the ionic bonds that are present within it, and therefore it's going to make the whole compound to be less ionic. The more polarizing power that is present by the given cation in an ionic compound, the lower is its ionic strength of the ionic bonds. So magnesium chloride is going to be less ionic as compared to sodium chloride. And if you are to also compare aluminum chloride has the lowest, because the cations, which is going to be the aluminum ion in aluminum chloride, has the smallest ionic radius, highest charge density together with the highest polarizing power. And by having all those three components, smallest ionic radius, highest charge density together with the highest polarizing power, that means that it's going to have the weakest bonds within its ions, and therefore we expect that aluminum chloride is going to be predominantly or partly covalent. And therefore, and you know the characteristics of covalent compounds, the covalent bonds always require a low amount of energy for them to break. And that's why it has a very low melting or boiling point. So the other explanation you're going to look at, which is going to be our Roman number 2, you're going to say that aluminum chloride dissolves in methylbenzene, but sodium chloride does not. And the reason for that, you're going to say that the aluminum ion in aluminum chloride has a higher charge density, or you can just say the aluminum ion in aluminum chloride has a higher charge together with a smaller ionic radius, which are the properties for it to have a higher polarizing power. So you're going to say that it has a higher charge density and a smaller ionic radius than the sodium ion in sodium chloride, and as a result, it has a higher charge density together with a higher polarizing power than the sodium ion, and therefore the chloride ion is going to be greatly polarized by the aluminum ion in aluminum chloride, and therefore we expect that aluminum chloride to be mainly or partly or predominantly. You choose one of the words that is easier for you. You either use mainly, partly, or predominantly covalent, and hence is going to be soluble in nonpolar solvents such as methylbenzene, because covalent compounds are soluble in nonpolar solvents. So since aluminum chloride is partly or mainly covalent, is going to be soluble in nonpolar solvents. But if you look at sodium chloride is mainly ionic, because the sodium ion there, it has a small ionic radius with a small charge, and therefore it has the least polarizing power and the least charge density. So we expect sodium chloride to be mainly ionic and to have full characteristics of ionic compounds, and we say that some of the characteristics of ionic compounds or pure ionic compounds, they are non-soluble, or they do not dissolve in nonpolar solvents such as methylbenzene. So we shall make a conclusion that, however, sodium chloride is purely ionic and insoluble in nonpolar solvents. So looking at Roman number 2, we are going to say that the melting point of Li2 chloride is 500 degrees Celsius, whereas that of Tin2 chloride is 247 degrees Celsius. Explain this observation. If you look at this question, they have set it in terms of melting points. And these melting points they have given us, you are seeing that anions are the same, but it's the cations that are varied. So since it's the cations that are varied, we start looking at the factors that affect cations on the anions that are common in each of the compounds. So we're going to say that Li2 ion in Li2 chloride has a larger ionic radius than Tin2 ion, and therefore Tin2 ion has a higher charge density. and polarizing power than the lead-2 ion in lead-2 chloride. So what you should know here is that whenever you are presenting explanations, we present them in terms of polarizability, and polarizability depends on ionic radius, the charge present. Now here, tin2 chloride and tin lead-2 chloride, they are present in the same charges, but both of them are group 4 elements, and one of them is above one another. If you look at tin and lead, you'll see that tin is above lead, and therefore we expect that tin has a smaller radius, ionic radius. Tin2 ion has a smaller ionic radius as compared to lead-2 ion, and we say that the smaller the ionic radius, the higher the charge density, and the higher the charge density, the higher the polarizing power. So that's what this explanation is trying to bring. So you're going to say that therefore tin2 ion has a higher charge density and polarizing power than the lead-2 ion, which makes the tin2 chloride mainly covalent, whereas lead-2 chloride is going to be mainly ionic. And since tin2 chloride is mainly covalent, that means that it's going to have the least melting point, because covalent compounds or covalent bonds need a low amount of energy for them to be broken as compared to the ionic compounds which are going to be present in lead-2 chloride, because lead-2 chloride is mainly ionic because the lead-2 ion has a larger ionic radius, and hence since it has a larger ionic radius, it's going to have a lower charge density, and therefore we expect that lead-2 chloride is going to be mainly ionic with strong ionic bonds which require a very high amount of heat or energy to be broken. Now looking at more examples, you're going to say that explanation number 4, lead-2 chloride is insoluble in ethanol, which is the same as nonpolar solvents, whereas lead-4 chloride readily dissolves in ethanol. So you're going to approach that in terms of explaining the other factors that we talked about. You talk about the charge, you talk about the ionic radius, and you talk about their effect on the polarizing power. So you're going to say that if you look at lead-2 chloride and lead-4 chloride, what is going to vary is going to be the charge. Lead-4 ion is going to have a +4 charge, and lead-2 chloride is going to have a +2 charge. Now, since lead-4 is having a +4 charge, we expect lead-4 to have a higher charge density as compared to lead-2 ion. And hence, since it has a higher charge density, we expect it to have a smaller ionic radius together with a very high polarizing power. And therefore, lead-4 chloride is assumed to be more covalent, and therefore it has to be possessing covalent characters for it to dissolve in nonpolar solvents such as ethanol. So let's start our explanation by saying that the lead-2 ion in lead-2 chloride has a smaller charge, and therefore it has a larger ionic radius than the lead-4 ion in lead-4 chloride. So we're going to say that therefore lead-2 ion has a lower charge density, and hence it has a lower polarizing power than the lead-4 ion. This makes lead-2 chloride to be mainly or predominantly ionic, and therefore it's going to be insoluble in nonpolar solvents such as ethanol, whereas lead-4 chloride is going to be mainly covalent because the lead-4 ion, it has a higher charge, smaller ionic radius together with the highest polarizing power. Therefore, lead-4 chloride is going to be predominantly covalent, and therefore it's going to have characteristics of covalent compounds such as being soluble in nonpolar solvents such as ethanol, which was given in the question. So looking at part number 5, or part 5, we are going to say that the melting point of calcium oxide is going to be higher than that of calcium chloride. And we're going to say that the reason for that is because the oxide ion in calcium oxide has a smaller ionic radius than the chloride ion in calcium chloride. So if you look at these two, calcium oxide and calcium chloride, what was varied was the anion, and since it was the anion which was varied, you remember what I told you. If at all they vary the anion, we explain in terms of polarizability, the ease by which anion can be, the electron cloud on anion can be distorted. So that's the point in which we explain this term in. So we're going to say that since calcium oxide and calcium chloride, they vary with the anions, we are going to be explaining in terms of the factors affecting the ease by which the electron cloud on the anions can be distorted. And to do that, we are going to explain in terms of ionic radius of the respective anions. So we're going to say that the oxide ion in calcium oxide has a smaller ionic radius than the chloride ion which is present in calcium chloride. And as a result, the oxide ion, since it has a small ionic radius, just like we said, is going to be less easily polarized by the cation, which is our calcium. But the chloride ion, having a larger ionic radius, is going to be more easily polarized by the calcium ion, and therefore we expect calcium chloride to be mainly covalent, and calcium oxide is going to be mainly ionic. So we're going to say that this makes calcium oxide to be more ionic, or the whole of calcium oxide as a compound to be more ionic than calcium chloride for the reasons explained above. And the ionic bonds in calcium oxide, remember that ionic bonds are stronger than covalent bonds. So ionic bonds in calcium oxide are going to require a higher amount of energy for them to be broken, so as to melt calcium oxide, as compared to that of the bonds, or the mainly covalent bonds that are present within calcium chloride. So looking at example 6, you're going to say that the table is going to show the melting points of the magnesium halides. So we have halide number 1 to be magnesium chloride with a melting point of 1263, and magnesium chloride to have a melting point of 714, magnesium bromide to have a melting point of 711, and magnesium iodide to have a melting point of 634. So we're going to be explaining the general trend in the melting points of the respective halides. Now proceeding or explaining about the table that you have just mentioned above. Now since I've already took you through all the process, let's be quick here. So if you look at what you have in the table, what has varied has been the anion. That means that we're explaining in terms of the ease by which the electron cloud on the anion can be distorted, which is called polarizability. And what determines polarizability is going to be the anionic radius, the ionic radius of the respective anions. The smaller the ionic radius of an ion, the less easily it's going to be polarized, and therefore such a compound is going to be mainly ionic. But the larger the ionic radius of the anion, the more easily it's going to be polarized, and therefore such a compound is going to be assumed to be covalent. So we're going to say that under explanation that melting points of the halides is going to decrease from magnesium chloride to magnesium iodide. Always first start by stating the trend of what they are telling you to explain. And we'll continue with the explanation by saying that this is because the ionic radius is going to be increasing from the fluoride ion to the iodide ion, which are present in the respective magnesium halides. And we say that the degree of polarization of the anions is therefore going to increase from the fluoride ion to the iodide ion. That means that fluoride ion is going to be less polarized as compared to the iodide ion. The iodide ion is going to be the one which is most polarized, since it has the largest ionic radius as compared to the fluoride ion. So we say that increasing the covalent character of the halides in the same order. So you can add the supplement here that in the same order from fluoride to the iodide ion. And you're going to say that that's decreasing the amount of energy that is required to break the magnesium to halogen bonds as you go down the halides, becoming increasingly more covalent. So that means that magnesium fluoride is less covalent than magnesium chloride, or magnesium chloride is more covalent than magnesium fluoride, due to the variation in the anionic radius. So what you're going to do about what you have covered about polarizability and polarizing power, you're going to write down these questions. Now, when you're writing down these questions, ensure that you discuss them with your friends fully and don't ignore any of the questions. After that, you take them to your teacher for analysis. So you pause the video and you take down each of these questions, and make sure that all the questions you take down, make sure that you don't proceed to the next heading without understanding how to answer either of them. Refer to the notes that have been given, also to the explanations, by replaying the video so that you can easily answer each of these questions, because these questions always come in a standard paper, especially paper 2. Because when you're studying that paper, we have what we call mixed questions. Mixed questions involve both knowledge of physical chemistry and inorganic chemistry. And these are the questions, or this is the topic, which is mixed from both physical and inorganic chemistry. So you have to be very good at interpreting the questions under it. So I pause the video and write down the respective questions as we proceed to the next heading. Now, due to the high polarizing power of the respective cations in the different ionic compounds, we expect such compounds to dimerize in air. Now, I'm sure that you have already had this term already in corrugative properties, which was already a topic discussed on this topic on this channel. So make sure that if you haven't covered it, you understand what you call dimerization. Now, in solution, we call dimerization association, as we call it in corrugative properties. But in air, association is known as dimerization, and it's as a result of the cations in ionic compounds having very high polarizing power or having very high charge densities that lead to high polarizing power. So first of all, you draw the structure of aluminium in this form on one plane, and you also add the structure of aluminium on the other side, and then we join the two structures using the two arrows. The arrow must be coming from a non-metal towards a metal, because it's non-metals that contain bonding electrons that go and form dative bonds or coordinate bonds with the atoms, with the metal atoms. So the structure for aluminium is the same as the structure for iron of their respective chlorides, and the structure for barium is going to be as follows. You also draw the structure of barium chloride on one side, and you also draw the structure of barium chloride on another side. And after that, you join with arrows. You join the two structures with arrows, but the arrows must be coming from a non-metal towards a central metal atom, from a non-metal towards a central metal atom. Reason is because non-metals contain free electrons or bonding electrons that can form dative bonds with the central metal atoms. And we're going to look more in details of drawing these structures under transition elements. So looking at the strength of a covalent bond, depending on the following factors, we are going to be determining or looking. Now we have been covering ionic compounds and how ionic compounds transit to covalent compounds. So in this chapter, we are going to be looking at the strength that affects the characteristics of the covalent compounds, or the bond length that is present, or bond strength that is present within the covalent compounds, and we are looking at the factors specifically affecting each of them. So we're going to start with bond length. Now remember that all these factors are very crucial in explaining melting points under inorganic chemistry questions, each and every question where there is a melting point. So you should be very attentive for you to understand them in depth. So we're going to say that, looking at the bond length, we're going to say that the shorter the bond, the more stronger it is. And the longer the bond, the more weaker it's going to be. And the reason for that is because when the bond length increases, the region of space that is present between the atoms. Remember that when you're dealing with a covalent bond, it's formed between atoms, not ions. If at all a bond is formed between ions, we call that one an ionic bond. When you're explaining covalent compounds, you explain in terms of atoms, or you explain in terms of atomic radius. So we expect that the larger the atomic radius, the longer the bond length, and the longer the bond length, the weaker it is. And therefore, the smaller the atomic radius, the shorter the bond length, and the shorter the bond length, the stronger it is. So we're going to say that the reason behind that, though it's not necessary when you're explaining melting and boiling points, let's look at it so that you just understand it. So this is because when bond length increases, the region of space between the atoms in which electrons are shared becomes proportionally smaller as the atomic radius increases. So we look at also the atomic radius as a factor affecting the bond strength of covalent compounds. Now remember that for bond length to increase, atomic radius has to increase. So these two go together, or they have relatively the same explanations. So we're going to be saying that the larger the atomic radii of the bonding atoms, the greater the bond length, and the lower the bond dissociation energy. The moment the bond gets longer, the weaker it becomes, and the shorter the bond length gets, the stronger it becomes. And what determines the bond length is going to be at the atomic radius. The larger the atomic radius of the bonding atoms, of each of the bonding atoms, the longer the bond and the weaker it is. But the smaller the atomic radius of the bonding atoms, or the atomic radii of the bonding atoms, the shorter the bond, and therefore the stronger it's going to be. All those factors are going to be very crucial in explaining melting and boiling points. So we're going to proceed by saying that the lower the bond dissociation energy, the lower the bond strength. And therefore, the smaller the atomic radii, the smaller the bond length, and the higher the bond dissociation energy. Bond dissociation energy, we have just looked at it under thermochemistry, which is the energy required to break 1 mole of a covalent compound into its constituent gaseous atoms. So you review thermochemistry videos to understand this in depth. So we're going to say that the higher the bond dissociation energy, the higher the bond strength, because more energy is going to be required, and therefore, since more energy is required to break such a bond, we expect such a bond to be very strong. Now let's look at the last factor, which is going to be electronegativity difference of the bonding atoms. And we're going to be saying that here, the greater the electronegativity difference between the bonding atoms, or the atoms that are covalently bonded, the greater the bond polarity, and the higher the bond dissociation energy. Now, bond strength increases with increase in polarity of bonds. Now we are going to be explaining this under acidity, or you are going to face this explanation under acidity, explaining acidity of the halides of the group 7 elements. And there we are going to see that when you're having covalent compounds, the higher the polarity between the two atoms, the stronger such a bond gets. But if you're dealing with ionic compounds, the higher the polarity between the bond, the weaker it gets. So don't get things wrong. Polarity increases strength in covalent compounds. The higher the polarity, the stronger a covalent bond gets. But if we are dealing with an ionic bond, the higher the polarity within the bond, the weaker it gets. So you have to be very good at identifying that, because that's where majority of the students get the confusion from when they're explaining acidity of group 7 elements. You try to review that explanation so that you can understand it properly. So the higher the polarity in covalent compounds, because all halides of group 7 elements are covalent compounds. And therefore, when you're explaining their polarity, we shall tell you that the bond between hydrogen and fluoride is highly polar, and therefore is the strongest. But when you're dealing with a covalent compound, such as aluminum chloride, and we tell you that aluminum chloride bond is highly polar, since it's an ionic compound, polarity just decreases the bond strength in ionic compounds. But in covalent compounds, polarity increases the bond strength. So when you're dealing with an ionic compound and polarity is high, bond strength is going to be very low. But if you're dealing with a covalent compound and polarity is very high, bond strength is going to be high in covalent compounds. So the takeaway here is that you should know that in covalent compounds, the higher the polarity, the stronger the compound becomes. But in ionic compounds, the lower the polarity, the lower the bond strength gets. So looking at the bond, concept number 3, we're going to look at the number of bonding electron pairs. So here we are going to say that triple bonds involve 3 electron pairs, and therefore they are going to be shorter and stronger than the double bonds, which involve only 2 electron pairs, and therefore which are shorter and stronger than the single bonds that only involve 1 pair together with similar atoms. And the example for that is going to be the following table. So the question is going to be as the following under that explanation, or about what you have discussed so far. So you're going to say that the respective bond energies of the covalent bonds of group 4 elements are given below. So the bond between carbon to carbon, silicon to silicon, and germanium to germanium, you are going to get the bond dissociation energy, which is the energy required to break. We defined bond dissociation energy in thermochemistry videos, and we said that bond dissociation energy is going to be that energy required to break a covalent compound into its constituent gaseous atoms. It's the energy required, it's not the enthalpy change. So that for carbon to carbon is going to be positive 330, is going to be 346, and that one for silicon to silicon is going to be 175. And that one for germanium to germanium is going to be 168. So you're going to be explaining the trend in the variation of the bond dissociation energies across the three group 4 elements. So you're going to state the trend in bond energy, giving a reason for your answer. And the reason is going to come from what you have already discussed above. And you're going to say that the bond energy decreases from carbon to carbon bond to silicon bond and then to germanium bond because the atomic radius is going to be increasing, or the atomic radius increases from carbon to germanium. And since atomic radius is increasing from carbon to germanium, remember that atomic radius increases down the group. And all these ones are in the same group, which is group 4. We looked at that in organic chemistry. And video for group 4 is already uploaded here. So you revisit it if at all you haven't mastered group 4 elements. So this is because the atomic radius is going to be increasing from carbon to germanium, and the more the atomic radius increases, bond length is also increasing. And we say that once bond length increases, also bond strength decreases. So that's a simple elaborative explanation for it. And such an explanation is going to be set in paper 1 and it's going to be given a maximum of 2.5 marks. So 1 mark is going to be for stating the trend, and the other mark will be for explanation. Always start by stating the trend, and then later you give your explanation, which must be starting with "this is because." Always take note of that. So question two we are given a table below containing bond energies of the hydrogen halides. So bond energy, remember that bond energy is universal. Bond energy can be defined in terms of dissociating or in terms of forming a bond. And we say that in thermochemistry, when you're forming a bond, energy is given out. But when you're breaking, energy is required. So if you are to define bond energy in terms of bond formation, you're going to say that this is the energy given out when 1 mole of a covalent bond is formed from its constituent gaseous atoms. So looking at the bond energies for hydrogen fluoride is 556, for hydrogen chloride is 431, and for hydrogen bromide is 336. For hydrogen iodide is 299. So we're going to explain the variation. If you look at the bond energies is decreasing down the group of the halides from fluorine to chlorine to bromine to iodide, and the reason for that is because of the same thing. All these ones are covalent compounds. Hydrogen fluoride is having the highest bond energy because it's highly polar, because it has the smallest atomic radius. All the atoms have a small atomic radii, and therefore they form short bond lengths, which require a very high amount of energy to break. So we're going to say that explain the observed trend in the bond energy, and we're going to explain it in that format. And we say that bond energy decreases from hydrogen fluoride to hydrogen iodide. And since these ones are covalent compounds, you explain in terms of atoms. Don't explain in terms of ions, you explain in terms of atoms. And this is what I've told you about acid strength, because they are combined compounds. So you're going to say that this is because the atomic radius. We are saying the atomic radius because combined compounds are explained in terms of atoms. Don't explain in terms of ions. When you explain in terms of ionic radii, that is, you will be explaining in terms of ions, which is not the case here, because you're looking at hydrides: hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. Once it's a covalent compound, we explain in terms of atoms. So that's why our reason is, this is because the atomic radius, we are using atoms because in covalent compounds we consider atoms combining. So the atomic radius increases from fluorine to iodine, and therefore bond length is also going to increase. And we say that the longer the bond, the weaker it is, and the shorter the bond, the stronger it is. So since bond length is increasing, we also expect bond strength to decrease in the same manner. And that's why you are seeing that these values are decreasing progressively from hydrogen fluoride to hydrogen chloride to hydrogen bromide, and lastly to hydrogen iodide. So you're given a sample question here for you to try out, and make sure that you try to discuss it with your friends so that you can come up with an elaborative explanation, answering it, and you take it to your teacher for verification. So the table below is going to give you bond energies of carbon to halogen bonds. So you're having carbon fluoride, carbon chloride, carbon bromide, and carbon iodide. Bond energies have also been given or attached, and you can see that they are decreasing progressively down the group, fluorine to chlorine to bromine to iodine. So using the given examples above, try to explain the observed trend under the bond energies in the above table. So pause the video and you take this question. So proceeding, we are going to be comparing hydrogen fluoride, water, and ammonia according to structure and bonding, or giving the explanations according to the explanation that is required from structure and bonding. So you're going to be looking at why their boiling points or their melting points are going to be varying. Now remember that when I was dealing with inorganic chemistry, I told you that the only 3 atoms in the periodic table that form hydrogen bonds is fluorine, oxygen, and nitrogen. When fluorine, oxygen, or nitrogen combine with an hydrogen atom, they form what we call hydrogen bonds. So the number of hydrogen bonds present in each of the compound determines its boiling point. So if you look at water, water is going to have 2 hydrogen bonds. If you look at fluorine, fluorine is going to have 1 hydrogen bond. So that's why the boiling point of water is greater than the boiling point of hydrogen fluoride. But if you look at ammonia, ammonia is going to have 3 hydrogen bonds. But however, its boiling point is way below that of water and that of hydrogen fluoride. Now let's look at the reason for that. So we're going to be saying that although fluorine is more electronegative than oxygen, meaning that hydrogen fluorine bond is going to be more polar. And I told you that so hydrogen to fluorine bond is going to be more polar than hydrogen to oxygen bond, and therefore hydrogen fluoride would have a stronger hydrogen bonds than water, because I told you that when you're dealing with combined compounds, the more polar a covalent compound is, the stronger the bonds within it. So we expect hydrogen fluoride to have stronger hydrogen bonds than those present in water, simply because fluorine is more electronegative, or it has a more smaller atomic radius as compared to the oxygen atom in water. So we say that this is not shown by the boiling points of the 2 compounds, and the reason is going to be of the following. So here the explanation, or the required explanation, is going to start from here. So you're going to say that water has a higher boiling point than hydrogen fluoride, because if you look at each water molecule, which I've already drawn up here, each water molecules form 4 hydrogen bonds. And you're saying that 4 hydrogen bonds because this is one water molecule. So if at all another water molecule combines with each other, we form what we call intermolecular hydrogen bonds together with hydrogen bonds. So each water molecule forms 4 hydrogen bonds, whereas each hydrogen fluoride molecule is going to form 2 hydrogen bonds. Now, as a result, the higher the number of hydrogen bonds present in a compound, the stronger the bonds within them are going to become, and therefore the higher the boiling point for such a compound. Now, since nitrogen is the least electronegative element among the 3, among fluorine and oxygen, nitrogen is the least electronegative element, and therefore the nitrogen to hydrogen bond is going to be less polar. And we say that when a covalent bond is less polar, that means that its bond strength is very low. So nitrogen to hydrogen bond is less polar than the oxygen to hydrogen bond, or the hydrogen to fluorine bond, and therefore ammonia is going to form weaker hydrogen bonds than those that are present in water or hydrogen fluoride. So that's the elaborative explanation for the variation in their boiling points. Now we are also going to look at the examples that are going to be explaining the effect of hydrogen bonding. Now we are going to look at example number 1, and we are going to be saying that explain why hydrogen fluoride is a liquid whereas other hydrides are gases at room temperature. So we're going to start with the answering, and we're going to say that the fluorine atom having the smallest atomic radius and the highest electronegativity among all the halogens is going to make the hydrogen fluoride bond more polar or highly polar. And we say that for covalent bond to be highly polar, that means that the bond strength within its bonds are going to be very strong, or it's going to be high. So we're going to say that the molecules of hydrogen fluoride are therefore held by strong intermolecular hydrogen bonds, which keep the molecules closer to each other. The stronger the forces keeping the molecules stronger to each other, the more likely is that with that component or that covalent compound to exist as liquid. Remember that most of the covalent compounds exist either as liquids or as gases. So those ones which have relatively stronger forces of attraction exist as liquids, and those ones that have weaker forces of attraction exist as gases. So we're going to say that whereas molecules of hydrogen chloride, hydrogen bromide, and hydrogen iodide are held by weak van der Waals forces of attraction, and these weak van der Waals forces of attraction, they are not strong enough to keep most molecules close to one another, but rather they are strong enough to keep them a bit distant from each other. And by keeping them a bit distant from each other, it's what makes the other hydrides of group 7 to exist as gases at room temperature, because their molecules are far apart, because they're held by weak van der Waals forces of attraction, with the exception of hydrogen fluoride, which is held by strong hydrogen bonds, which keep the molecules close to each other, and therefore hydrogen fluoride mainly exists as a liquid. So looking at number 2, we are going to say that the table below shows boiling points of group 7 hydrides. So hydrogen fluoride has a boiling point of positive 19.9, hydrogen chloride has a boiling point of negative 8.5, and hydrogen bromide has a boiling point of negative 66.7. Negative hydrogen iodide has a boiling point of negative 35.4. Now notice that here, among all the hydrides of group 7, it's only hydrogen fluoride which has hydrogen bonds between its molecules and its atoms, and therefore we expect it to have stronger boiling points, higher boiling points, because the hydrogen bonds require a high amount of heat to be broken. But if you look at other hydrides simply have simple molecular structures. And I say that whenever you're explaining melting points and boiling points, you talk about the structure. That's the first thing, the forces holding the structure, and then the factors on which the forces holding that structure are going to depend on, such as the atomic radius, because the atomic radius is going to determine the bond length. And we say that the shorter the bond, the stronger it is. The longer the bond, the weaker it is. So let's explain that in details. So explaining the variation in boiling points, including any anomalies involved, we are going to start by saying that boiling points generally increase from hydrogen chloride to hydrogen iodide, with the exception of hydrogen fluoride. And we are going to say that, however, hydrogen fluoride has an abnormally high value of boiling point. So let's start by explaining the general point. So we are going to say that the increase in melting point from hydrogen chloride to hydrogen iodide is because the hydrides are held by have simple molecular structures. So we have listed the structure. Then we follow it with the forces holding such a structure, which is held by weak van der Waals forces of attraction, whose magnitude. So we talk about the forces holding our structure are with van der Waals forces of attraction. Then we talk about what affects the strength of such forces. So we say that whose magnitude can also mean strength. So don't confuse this word in case you don't know it. Magnitude can also mean strength. So whose magnitude increases with increase in molecular weight, leading to an increase in the amount of energy which is required to break the forces. So explaining the number of hydrogen fluoride, we are going to say that hydrogen fluoride has an abnormally high melting point, and the reason for that is because the fluorine atom has the smallest atomic radius together with the highest electronegativity, so making the hydrogen to fluorine bond highly polar, and the more polar it is, the stronger it is. But also, hydrogen fluoride molecules are held by strong intermolecular hydrogen bonds, which require a very high amount of energy to be broken, and therefore hydrogen fluoride has an abnormally high boiling point as compared to other hydrides. So looking at other explanations which are going to involve hydrogen bonding, we are going to look at explanation of why 2-chlorophenol is less soluble in water as compared to 4-chlorophenol. Now the reason for that is going to be because of intermolecular hydrogen bonds and also intramolecular hydrogen bonds. Now the quicker difference here is that intramolecular hydrogen bonds are formed between the same molecule. The same molecule forms what we call the intermolecular hydrogen bonds. But for the intermolecular hydrogen bonds, they are formed between two molecules. Two molecules when they unite. For example, this is the water molecule uniting with a 4-chlorophenol molecule. So the two molecules form what we call the intermolecular hydrogen bond. But if the hydrogen bond is formed between the same molecule, we call them intramolecular hydrogen bonds. So the explanation for that is going to be as brief as follows. So you're going to say that, so this is going to vary according to the strength of the intramolecular hydrogen bonds and also the intermolecular hydrogen bonds. But usually, intermolecular hydrogen bonds are stronger than intramolecular hydrogen bonds. By looking at this, you're going to say that molecules of the 2-chlorophenol from the intramolecular hydrogen bonds, because the chloro group is near the hydroxyl group, is going to suppress the hydroxylic character of the compound, which prevents formation of the intermolecular hydrogen bonds between 2-chlorophenol and the water molecules, reducing its solubility. But however, molecules of 4-chlorophenol cannot form intramolecular hydrogen bonds. So the moment we resist formation of intramolecular hydrogen bonds, we increase solubility of that specific aromatic compound. So however, molecules of 4-chlorophenol cannot form intramolecular hydrogen bonds because the chloro group is far from the hydroxyl group, and therefore molecules of 4-chlorophenol form intermolecular hydrogen bonds with water, and formation of intermolecular hydrogen bonds with water increases what you call solubility. Now the same explanation is going to happen with the same question, though we are going to go it over quickly since we have already introduced the concept. So we're going to be saying that the boiling point of 2-nitrophenol is 214 degrees Celsius, whereas that of 3-nitrophenol is 290 degrees Celsius. So we draw the structures. For those ones, for 2-nitrophenol, the nitrosyl group is close to the hydroxyl group. So the two form what we call the intramolecular hydrogen bonds, which is said that is going to be the type of the hydrogen bond formed between a single molecule. But the intermolecular hydrogen bonds is formed between two different molecules. So let's look at the explanation under that, and we're going to say that molecules of 2-nitrophenol form intramolecular hydrogen bonds because the nitro group is nearer the hydroxyl group. So as a result, this is going to suppress the hydroxylic character of the compound and is going to prevent formation of intermolecular hydrogen bonds between the 2-nitrophenol molecules. Hence, only weak van der Waals forces of attraction are going to be holding such molecules. Now remember that I told you that intermolecular hydrogen bonds are stronger than intramolecular hydrogen bonds. So once intramolecular hydrogen bonds are, formation of intramolecular hydrogen bonds lead to prevention of formation of the intermolecular hydrogen bonds which are the strongest. So that means that compounds with intramolecular hydrogen bonds are going to have low melting point because they are going to be joined mainly or predominantly by van der Waals forces of attraction, which require a very low amount of energy for such molecules to be separated. But formation of intermolecular hydrogen bonds, which are the strongest within two different molecules, is going to increase the boiling point. Reason being, these bonds require very high amount of energy for them to be broken. So we're going to continue and say that, however, molecules of 3-chlorophenol cannot form intramolecular hydrogen bonds because the nitro group is far away from the hydroxyl group, and as a result, molecules of 3-nitrophenol therefore are going to form intermolecular hydrogen bonds, and these bonds are stronger, hence are not easily broken, and therefore such a compound is going to have a very high boiling point. So according to what you have covered, you're going to pause the video and then you write down these questions. Now these questions, for you to understand them properly, you make sure that you have a discussion group. After getting a discussion group, you share the video and you make sure that all your group members have fully understood the concepts that have been discussed. And after that, you try to discuss each and every part. Make it a habit to discuss each questions of chemistry every day so that you can get good at the concepts. And that's interpreting the data that is going to be presented at the end in your final examinations. So make sure that you copy these questions and you organize them in terms of a discussion before you answer them. It's a discussion first and then you answer them last. So you pause the video and you take down the questions. Now looking at the strength of the metallic bond, we are going to say that the strength of a metallic bond is going to be determined by the following three factors. So one is going to be the charge that is present on the cation, and secondly is going to be the number of localized electrons per atom, and the other one is going to be ionic radius in case we are dealing with an ionic compound. But if you're dealing with elements, we talk about number of localized electron contributed per atom, and we looked at this explanation under group 2 elements. So we're going to say that for the charge of the cation, we're going to say that the higher the cationic charge, the stronger the metallic bond, because there will be a stronger attraction for the localized electrons. And explaining number 2, you're going to say that the higher the number of electrons contributed per atom towards metallic bonding, the stronger the metallic bond gets. This is because there will be a greater attraction between the nucleus and the localized electrons. And factor number 3, you're going to say that the smaller the ionic radius of the cation, the stronger the metallic bond, because there will be a stronger attraction for the localized electrons. So looking at two examples under that, you're going to say that to explain why the melting point of chromium is higher than that of calcium. So first of all, we are going to first write the electronic configuration since we are explaining elements. When you're explaining elements, you first write down their electronic configuration so that you can see what is going to be talked about. Remember that we looked at this under periodicity, so you're just giving a review of it. So electronic configuration for calcium is going to be as follows. I hope you know how to write electronic configurations. That one for chlorine of chromium is going to be also as follows. So let's look at the explanation that can be given under that. So we are going to say that calcium has a large atomic radius and only contributes 2 electrons from the 4s sub-energy level per atom towards metallic bonding, and therefore it's going to form weaker metallic bonds that require a lower amount of energy to be broken as compared to chromium, which has a smaller atomic radius, and it also contributes both the 4s electron which is present in the 4s sub-energy level and also all the 5 3d electrons, forming stronger metallic bonds because it contributes more electrons per atom towards metallic bonding, and therefore its bonds are going to require a higher amount of energy to be broken. So looking at the last example under that, we are going to say that explain why group 2 elements form metals with higher melting and boiling points than the group 1 elements. So we're going to say that group 1 and group 2 elements form metallic bonds. Both of them form metallic bonds, but the strength is going to depend on the number of electrons contributed per atom for metallic bonding or for the formation of metallic bonds. And we're going to say that group 2 elements only contribute 2 electrons per atom, and therefore they are going to form stronger metallic bonds than the group 1 elements, which only contribute 1 electron per atom for metallic bonding, and therefore they are going to form weak metallic bonds. So since group 2 elements form stronger metallic bonds, they are going to require a higher amount of energy for their bonds to be broken as compared to group 1 elements, which only contribute 1 electron per atom and form weaker metallic bonds, which require a slightly lower amount of energy to be broken. Now this brings us to the end of this video. Your advice: share the video to your friends, subscribe to the channel so that we meet in the second part of structure and bonding. Now this video is going to be divided so that we cover structure and bonding in details, providing all the insights that are required for us to get the A in chemistry. So for those of you having exams or who are watching this before your final papers, I wish you success in your exams. Share the video to your friends and make sure you all benefit as a group.